Okay, so here we have a 2 kilogram mass on a 25-degree incline, and this mass has been compressed 0.4 meters into the spring, and it starts from rest. The spring is going to launch the mass up the hill. We're given the spring constant of the spring as 500 newtons per meter, and we're also told that friction is present between the block and the incline, and the coefficient of friction is 0.3. The thing we're solving for is the distance up the incline, measured along the incline, the distance the block will travel before coming to rest. And we're going to do this with work and energy. So the idea with conservation of mechanical energy is that mechanical energy initial equals mechanical energy final, but looking at it this way, this is only true if gravity or springs are the only forces affecting the motion. So in this problem, we have what's called a non-conservative force, and the non-conservative force in this problem is friction. And any non-conservative force is going to make this statement that I have circled here not true. The mechanical energy initial is not equal to the mechanical energy final, because what happens in this problem is friction is going to take some of the initial mechanical energy and take it away, convert it to heat energy. So we have to account for friction being present, and the way we do that is by taking this equation and accounting for the work done by the non-conservative force. So mechanical energy initial plus or minus the work done by the non-conservative force is equal to mechanical energy final. Now in this problem, the non-conservative force, as I mentioned, is friction. So I'm just going to erase the NC here, and we're going to call it what it is. And it's going to be minus. The work done by friction, it removes energy from the object. So we're going to call it minus. So we have mechanical energy initial minus work of friction is equal to mechanical energy final. And of course, there's three forms of mechanical energy. When I say mechanical energy, I mean kinetic, potential of gravity, and potential of spring. And same thing over here. Those three energies. All right, so let's take a look at our energies. And the first thing we should do is define the 0 point for this problem. And the 0 point is where we measure h from. Potential energy of gravity is mgh, and h is measured from what I call the 0 point. And all the 0 point is, it's where we measure h from, but the best place to put it is at the lowest point in the problem. So the 2 kilogram mass is smushed against the spring. This right here marks the lowest point for the mass. So we're going to say that this red line here is our 0 point. So then the h, when the block goes up, up, up the hill to this point here, our h is going to be this distance right here, which we can express in terms of d, where d is the hypotenuse. So this is 25 degrees right here. So h, using trig, we have a triangle. So h is going to be sine 25 times d. And we're going to use that in a minute. Okay, so let's go back to our energies. So kinetic energy initial is 0. When the block starts down here, it's starting from rest, so there's no kinetic energy. Potential energy of gravity initial, 0, because the block is starting on the 0 point, right here on our red line that we defined as h equals 0. This red line is h equals 0. Okay, potential energy of spring, we definitely have that because the spring has been compressed and there's energy loaded in it. Friction does work, so we're going to leave that alone. As the block slides up the hill, friction is removing mechanical energy, so we're going to say minus work of friction. Okay, let's look at the energy final. At the top of the hill, when the block reaches its highest point, it comes to rest for a brief moment. So the kinetic energy up there is 0. We can cross that out. Potential energy of gravity is present because the block is above the 0 point. And then potential energy of spring, we don't have it because there's just no spring up here. So what we have left is potential energy of spring initial, take away the work that friction does, and we're left with potential of gravity. All right, now plugging in the equations. Potential of spring, the equation for this is 1/2 kx squared. Work of friction is going to be the force of friction multiplied by the distance. And just a quick comment here, we're going to start the free body diagram. So if we look at the block as it's sliding up the hill, mg points down, normal force points straight up. So this is mg, this one is normal force, and friction is opposite motion and parallel to the surface. So the point I want to make here, when you do this work equation, work equals force times distance, the force and the distance always have to be parallel, which they are. If we look at the frictional force and the distance, these are perfectly parallel to one another, so we're in good shape there. All right, potential of gravity is mgh. Okay, so we're going to have to deal with friction because we don't know it yet. We do not have the force of friction, and h, we've already dealt with it right here. H is sine 25 times d, so that's going to get plugged in right here. So let's find our friction force. So friction has an equation. Friction is coefficient times normal force. And we already have the coefficient. It's 0.3. The thing we have to find is the normal force. So the way we're going to do that is by summing forces. We have to sum forces to get the normal force. And remember, on an incline, we always tilt the xy axis. So we're going to say that's the x direction, and then perpendicular to the incline is the y direction. So with a blue pen, I'm going to show the components of mg. So this guy right here is mg y component, and this angle in here is the same as the incline, so that's 25 degrees. All right, so what we're going to do is we're going to sum the forces in the y direction, remembering that we tilted the xy axis. We have normal force pointing perfectly in the y, and then the y component of mg is this guy right here, and that's going to be cosine 25 times mg. Sum of the forces always equals ma, or that's a y acceleration. And we do not have a y acceleration because the acceleration of the block is on the incline, which is the x. So perpendicular to the incline, there's no motion. So now we can solve for normal force. The normal force is cosine 25 mg, which is going to be cosine 25 times 2 kilograms times 9.8. which gives us a normal force equal to 17.7636. All right, so now we take the normal force, plug it in up here. Again, we're trying to find friction because we need it for this equation. So the coefficient is 0.3. That was a given. We just found the normal force, 17.7636. And this gives us a frictional force of 5.3291 newtons. All right, so to this equation here, I'm going to rewrite this one more time. 1/2 kx squared minus friction times distance equals mg. Now let's plug in for h. H is sine 25d. So the only thing missing in this equation now is d. So doing the algebra, which I'm not going to show in too great a detail, but if you do the algebra, you're going to get 1/2 kx squared divided by friction plus mg sine 25. So now we plug numbers in. This is going to be 1/2, our k is 500 newtons per meter. X is 0.4. Make sure you square the x. Friction we found to be 5.3291 plus, so m is 2 kilograms, gravity is 9.8, and sine 25. So you punch this into your calculator and you get a d value. Our answer for how far the block slides up the incline comes out as 2.938. Which is the final answer to this question. All right, so here we are doing part 2, which is finding the velocity of the mass when it's halfway up the incline. So let's put the block here on the incline, about halfway up, right there. And what we're trying to find is the velocity at that point. How fast is the block moving halfway to the top? So our d was the full distance all the way up the incline. We found that in part 1 to be 2.938 meters. And then the other thing we found was the force of friction. As the block slides up the incline, friction is acting on the block, and that's a non-conservative force, meaning that it's gonna make the initial mechanical energy and the final mechanical energy not equal to each other because friction steals energy. So let's replace our d value in the problem here. I'm gonna erase this, and we're gonna put in our new distance because we're only going halfway up the incline now. So to this point right here, half of the original d, so all the way up the incline, is 2.938. So half that distance is 1.4692. 1.4692. So all I did is I took this distance and divided it in half. Okay, so let's look at our energies. Before we look at our energies, we should set our 0 point. So we'll do this in red again. This is going to be the same thing from the first part. The 0 point, the best place to put the 0 point is the lowest point in the problem. So this red line is the lowest point for the 2 kilogram mass, which makes our h this. So we can solve for what h is. This angle here is 25 degrees. The hypotenuse is 1.4692. So h is going to be sine 25 times 1.4692 meters, which gives us an h equal to 0.6209, which we'll be using shortly. All right, so let's look at our energies. Again, the block down here, this is the initial point. There's no kinetic energy. It starts from rest. There's no potential of gravity because it begins on the 0 point. We do have potential energy of spring because the spring has been compressed. Friction does negative work. It's removing mechanical energy from the object. Okay, the final energies. Now we do have kinetic final because right here, this is our final. This point right here, halfway up the incline, is now the final, and it's in motion. So there is kinetic energy. We do have potential of gravity because the block is above the 0 point, and there is no spring energy because there's no spring at that point. So what we have is this. This is our master equation here. So what we do is we plug in the formulas. So potential energy of spring is 1/2 kx squared. Friction, the work of friction is friction times distance, and we have both of those. Our new distance is 1.4692, and we found the frictional force in part 1. and then this is equal to kinetic final, which is 1/2 mv final squared, and then potential of gravity is mgh. So at this point, the only thing that we don't know is v final. So doing the algebra, so what I did is I'm gonna multiply everything by 2 to get rid of the 1/2s, and then solve it for v final. So I'm just going to do this in one step to make the video a little shorter. So if you do the algebra correctly, you get v final equals square root kx squared minus 2 frictional force times distance minus 2 mgh, all divided by m. So then we plug numbers in, v final. So our k is 500 newtons per meter, x is 0.4, frictional force is 5.3291, the distance is 1.4692, minus 2 times 2 kilograms, gravity is 9.8, and then sine 25. Barely made it. Okay, then we divide all this by the mass, and this is all inside the square root, and then the mass is 2 kilograms. So v final, when you punch this into your calculator, comes out to be 4.4722 meters per second, which we could just round this to, I don't know, 4.5.